Leuven, with a thesis focused on gas exchange modeling in a fruit using diffusivity maps computed from X-ray CD images, a topic that strongly aligns with the themes we've discussed today. His recent his research focused on agricultural technology, food engineering, and bioprocessing with recent publication on rheological properties of fruits, non-destructive agricultural product assessment, and porosity quantification using X-ray CD and spatially resolve techniques. We're excited to hear how his work builds on today's earlier insights and brings an applied local context to AI integration in post-harvest engineering. Okay. Dr. Bayu Nugraha, the floor is yours.
Okay, check. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Hope that you are still eager to follow these courses. Unfortunately, Dr. Pieter Verboven do not appear in this lecture. We don't know why, but me and Dr. Pieter Verboven were at the same group at KU Leuven. So yeah, probably the course material will be more or less the same or in line with the Pieter Verboven as well. Okay. How many of you originally from Yogyakarta? Oh yeah, you're a student here, and Carlo as well. And the operators is my students. And most of you I heard from Philippines. Can you raise your hand? From Philippines, okay. And how many of you are from agricultural technology? 1, 2, 3, 4, 5, okay. Quite a lot. The commuter, yes, of course, yes. I know. Okay, this afternoon I'm going to talk about computer-aided food engineering, the next step for food process and handling optimizations. This is a little bit different from the previous courses. There's just more AI things, but these things is before the AI one. So in the future, the computer-aided food engineering will be an opportunity to be integrated with the artificial intelligence. But before you do a computer-aided food engineering using AI, you should know the background of computer-aided food engineering, or we can call it CAFE. Okay, I will talk about my profile. My research field is post-harvest engineering, especially in computer-aided post-harvest technology, and also non-destructive evaluation, typically using X-ray computed tomography. If you know X-ray, probably if you guys from abroad, from Malaysia, Philippines, you come to Indonesia, and in the airport, your luggage will be checked with the X-ray computed tomography. Then if you bring some things, then the operators will know. So be careful. Don't take so many gudeg or bakpia from Yogyakarta, they will know. And 3D modelings, we do some computation with the three-dimensional geometry of food products and fresh products. And transport phenomena. Transport phenomena means like if you boil egg, the transport phenomena happens during the boiling. Yeah, for example. And if you heat I don't know, coffee, maybe, with the microwave, and transport phenomena is also happen. So my research group is computer-aided post-harvest technology, CAPT. You can follow the Instagram, and this is my email and also email of my research group as well. Okay, contents of these courses will be introduction, CAA, it's computer-aided engineering, input engineering, modeling framework, future directions and opportunities, and conclusions. So we start with the introductions. What will you do to get the best performance of this storage chamber? I know you are mostly from agriculture, so you know the agricultural products. Yeah. And then imagine that the product already harvested and then stored in the cold storage or maybe some storage building, but you want to know the best performance of the storage chamber. So this is control atmosphere storage. How many of you already knows about control atmosphere storage? Okay, 1, 2, only. It's typically storage that can be modified. The atmosphere can be modified. The oxygen should be lower and the carbon dioxide a little bit increase and temperature is decreased to extend the shelf life of the products. Okay, this is, imagine that this is the new storage building. Then we want to know the performance of this storage. What we did before, we do experimental storage. Try to store onions or salad inside the CA storage. And we put so many onions inside the storage. We want to know how long the onion will be safe inside the CA. Okay. But we need so many onions. And also we need the facilities as well. Okay, we are going to start about the computer-aided engineering. This is prototype-based design. Probably when you are kids, you at least ever built these toys, maybe. And then we do experimental performance tests to check like aerodynamic tests, workload, efficiency, durability, and etc. But when it's failed, you need to redesign and recreate the prototype. So you need money again. You need the materials again. If you are not happy with the new design, you need to make another one. Okay. So we move to model-based design. You create design on the computer, and then involving simulations and virtual representations of the object for optimization. You do this performance test inside the computer. And then you can find out the best design and readily create it. Then you can come to, I don't know, the 3D printing or something, then you can build your design with the best performance after you do some simulations using the computer. Food product, process, and equipment design, like our other manufacturing, is typically start with building, testing, and improving a prototype based on feedback. For example, here, you process bread, you have to mix, stir, and then shape oven, and then make it ready to be eaten. And then consumer will give you feedback about the texture, smells, looks, or appearance, and also taste. And then you need to recook the bread to make better versions of the bread with the good texture, good smells, looks, and also delicious taste, as you expected. Okay, food manufacturing involves unit operations at mixing, emulsifying, heating, drying, baking, puffing, and packaging. And here, impact to final quality, food safety, and cost effectiveness. Okay. Okay, mathematical equations should be introduced in this step to get better final quality, good food safety, and cost effectiveness. With the process or product parameters like a temperature, relative humidity, moisture content as an input, and then quality and safety parameters like a color, texture as an output. Food process models can be approached in two ways: mechanistically or based on data. The mechanistic models or mechanistic mathematical model are built on well-known physical principles such as energy and mass conservation. This is, yeah, you can imagine that these are the fruits like apple, maybe. Apple undergoes respiration after harvested. And then some airflow will hit the apples and convection happens. And at the same time, also the conduction, heat conductions also happens. This causes liquid and vapor diffusion from the apple to the environment. So the weight of the apple will decrease. And then also shrinkage at the same time happens. Radiations, absorption, and emissions also play roles in this reaction, microbial growth, and thermal damage. This affects quality attributes like firmness, weight loss, pale shriveling, pale and flesh color, chilling injury, respiration rate, and others. So most food processes are complex enough that they cannot satisfactorily represent it using such analytical models. So this is what you do to check quality of your food during process or cooking. You check the temperatures, you check the texture, whether it's overcooked or undercooked, or it's already well done, so it's ready to be consumed. Okay, this is more complex model incorporating additional physics evolve. Okay, I will skip this. And then computer-aided engineering in food process or in food engineering. Yeah, we can call it now as a computer-aided food engineering. CAFE includes building a virtual or computer models of physical product, process, and equipment, and simulations of these models to guide decision-making in design with goals such as improve quality, safety, and reduce time to market. Okay, this is raw materials. Let's say the chicken. And then this is expected quality of the chicken after cooking. Okay, the computer-aided food engineering plays in this position. But we require mathematical models, product and process parameters, product and or equipment geometry. Models always, this is previous computations in food process. Old computations, let's say. A model always involves simplifications of reality and compromise between the real process and required computational effort. And also precursors to computer-aided models were simpler models such as LAM parameters that ignore spatial variations inside the food, or models of simple process with simple geometry. For example, here is a slice of meat. You know that it can be simplified with the simple geometry like a block. However, the meat consists of fat, bone, proteins, and some air inside the meat. So the fact is, this is not the same. If you're using a box to simplify the geometry of the meat, it's not exactly the same. The fact is, at micro scale levels, this is the image of the meat at micro scale levels. You can see fractions of proteins, fat, and air. So forget about single continuum. We move to the complex things now. Food structure are physically heterogeneous. Okay, also apple. It can be simplified with the spears. Simplified shape of the apples. Yeah, okay, apples is almost spheres, but it's not exactly the same. Deviations between the two exist. Okay, there's some gaps here, as you can see. Yeah, this product is not materials built in like I don't know, mechanical engineerings or in another engineering fields. The shape of the foods is irregular. So modeling in the food process is not that easy. Okay, here, you know this fruits? Do you have some star fruits in Vietnam? Yes? And do you know this? Snake fruits? The skin is like snake. Yeah. And probably in Malaysia, did you find this kind of fruits? Yes? Snake fruits? In your country as well? No, no, you didn't have that. Okay. Others? Philippines? Do you have snake fruits? Have you ever seen before? Here? Have you tried it? Okay. You like it? Yeah, but the skin has a bit, yeah, it's like snake. It's called snake fruits. And others, the shape is irregular. So also inside the fruits, the structure is heterogeneous. You can see this is the apples during the storage and the crate. And if we zoom out, zoom in, make it bigger, and then getting bigger, and then we now already in the apple tissue. Okay. And then this is the cell structure of the apples with some air in between the cells. So this is Verboven. Yeah. Actually, the previous, it should be the previous um, lecture. Okay. So the structure range from macro to micro. We can call it as a multi-scale structures. Simplifications in models, physical and chemical properties, geometry may bias the result, leading to wrong decisions in food process and handling optimizations. Okay, we move to modeling framework. Yeah, it's a bit, a little bit difficult, but I hope that you can follow. I simplified this lecture to make it more general. Okay, fundamental principles of conservation of energy and mass combined with constitutive equations that relate the transport of a quantity to its driving force, like a Fourier law of thermal conductions, mass diffusions, and pressure-driven flow. All of them are core building blocks of mechanistic models. Because if you applied the computer-aided food engineering or computer-aided engineering in your life, then you need to know these basics first. The mechanistics models, okay, as you know that the fruits range from, or food range from the macro scale to the micro scales. Yeah, incorporating structure, geometry, microbial, chemical kinetics, and compositions. And mechanistics models, like these are apples. And if we create a line and radius of the apples, like here, and then measure the porosity of the numbers of pores. Then it varies with the distance from the peel to the centers. So it's heterogeneous. The structure is not the same in the entire apples. Yeah, this is some mechanistics models that here you need to implement the gas transport and then with the diffusions that take into account the variability of the tissue microstructures. And multi-scale modeling. Why the multi-scale modeling? This is a chili paper. The virtual geometry of chili pepper at the macro scale levels. And this is the virtual geometry of chili pepper at the micro scale levels. Actual geometry. In multi-scale modeling, we know homogenizations, its physical parameters such as effective diffusivity calculated at the micro scale levels is used to compute gas transport at macro scale levels. And localizations, its local phenomena at the macro scale levels is followed up at the micro scale levels. However, some years ago, we developed a method to map the micro scale parameters like porosity, diffusivity, and others micro scale parameters into the macro scale levels. So now we have maps of the porosity that we know as an micro scale parameters map at the macro scale levels inside the chili. And we move to thermal conductivity maps as well. This is very important to analyze heat transport inside the chili during the storage, let's say. And then we implement the heterogeneous physical parameters based models. For example, here, using the uniform gas diffusivity and using heterogeneous gas diffusivity. And then we do some computations here. With the uniform one, the RQ or respiratory quotients, this is the indicators of the quality of the product. So if the RQ reach or above 1, the product should have be damaged. Let's say here, it's more than 1. At the simulations using heterogeneous diffusivity. And then the simulations compared to the actual defect that we found using X-ray computed tomography. This happened. It's predicted. Okay, we can know that the product will be damaged before the storage is started. Okay, this is after the storage. We can do these computations before the storage. And it happens. Okay, and for and also the applications for the storage, we back to the controlled atmosphere storage. Let's say oxygen concentrations on the air is 21%. We have safe limit. If we decrease the oxygens at least above the safe limit, so the product will stay 1 year, let's say, for the best settings of the control atmosphere storage. But we decrease oxygen concentrations below the limits, then defects will come out. It's visually undetected. You cannot see the defect using your eyes. It will be the same with the sound fruits. So it's undetected. We do these computational things to optimize the onion storage. We create the geometry of the onions, the stack of onions, okay? And then we compute the gas level, the oxygen level inside the onions. Because if we puncture the product with the needles or sensors inserted into the product, then the cells will damage and the respirations will immediately stop. And what you measure is something biased. If we do these things with improper method. So instead of do the measurement experimentally, we simulate the oxygen level inside the product. And then, yeah, we can predict it. We can predict the internal breakdowns inside the onions, and these conditions, oh, sorry. Next. It's validated with the observed internal disorder inside the onions. And also this is the snake fruits. We do some computations also in the snake fruits. This is the temperatures. And also moisture contents. Yeah, here the data is gained from simulations only. We can know the decrease of water content during the storage period, and then, this is the weight loss and also thermal conductivity. So the computer-aided food engineering steps start from, we know the raw materials, process, and equipment. We create the models and do simulations with, of course, right method of the simulations using right mathematical models to avoid under or overcook, and also consistent quality, improve quality, personalizations, and make decisions making. Future directions and opportunities of the computer-aided food engineering: increase community resources for food computations. Yeah. And multidisciplinary training, because this is quite, now is still rare, the expertise in this area. And share opportunity and geometry database. This is what another university do with the share properties and geometry database that can be used for many researchers. Easier integrations with the material or geometry transformations, faster simulation, reduce order models. Yeah, as we did with the microscale parameters mappings, is the things to reduce the simulations, and also cloud computing. Integrations with systems level approach, and the last one is AI integrations. This will play a role in real-time optimizations, parameters estimations, decision making in food manufacturing system and seen as a powerful complementary tools within broader cafe frameworks. So, multidisciplinary human resources are scarce now. Operating at interface of engineering and food science, cafe is inevitably this area. Who is here from food technology? Okay. So you need the engineering skills as well to integrate the food science knowledge and the engineering things to be expertise in this area. good things to start. You know what is the conductions, what is the convections, what is the diffusions, thermal conductivity, and many others physical parameters that involve in this area. Because if we don't have any informations about that, then the result of the computations will be out of uh, precision's result, precise result. And then the next one, you can use, of course, computer-aided design or CAD. You can learn CAD like you designed, I don't know, storage, or you can design oven maybe, or other equipments that you want. If your designs is good enough and detailed enough uh, as the reality, and then more precise the result you get. The other ones is you can learn and combine with the other simulations models and the softwares. But the challenge is in foods or in biological materials, the products is react. Yeah, it's not diet materials. It's react with the environments, with the process, with the temperature, with the relative humidity. So you also need to learn the chemical reactions, or food science is also important basics beside the engineering things. Then you can combine all these things to be expert on computer aided food engineering. That's it. Yeah.
Okay, thank you. Anyone who wants to ask the question? Or maybe from the online participants? No? Or while we're waiting for that, can I ask a question to it? Maybe, yeah. I guess maybe the online participants still writing or typing on that. So, have you encountered challenges like playing simulation models from the lab scale to the pilot scale or even in the industrial level? Yeah. Have you ever encountered, and can you share on that? And how do you feel about the scalability?
Okay. Scale up the simulations from the lab scale to the actual pilot or industrial scale. Yeah, it's just actually one of the challenge in computer aided food engineering. Yeah, but as far as you do the precise computations at the lab scales, it actually can be applied or validated at the industrial or pilot plant scales. For example, you can do the simulations, start with the small scales, and then you do validations at the same scale of that, at the same scale of the computational one, experimentally, and then you move to the bigger scale. If the small scale are valid, then you can move to the bigger scale. You can do sensitivity analysis. There's the things that I did not explain here is the optimizations of the simulations. We can use the sensitivity analysis, let's say Monte Carlo analysis and other sensitivity analysis things to check how big our simulation should be. Because in engineering concept, you don't need to go into quite detailed simulation, but at the same time, you don't do a coarse or bad simulation. So in the middle between these two, it's the good things as an engineer to do simulations.
Okay, everyone, like, okay.
My name is Helmi, and I'm from and I this technology the computer it can be implemented in the process sterilization units such as record or ultra high temperature currently working on the high temperature or high pressure. And I have an experience with record small scale units. And it's the experience I really want to know what happens in the can when we sterilize the product. But we also can know the finished product after we open the can. After we offer the sterilization process. Okay. This can be implemented. Okay, thank you. Interesting. It of course can be implemented as far as you know all the parameters during the process, during the retort process, sterilizations and other things. And you have good parameters of the products. You have input data from the environment of the retort, like temperatures, pressure, relative humidity maybe, and other things, and combine all the parameters. And you have good design of the cane and the food inside the cane as well, the parameters of the cane materials, parameters of the food materials inside, and you can do the simulations in the right way. Yeah, I think it's it's opportunity for the next research. And if you want to see how the process in the real time during the in one side the sterilizations is going on, and at the same time you can see the virtual sterilizations. You can do digital twins. It's in Indonesia it's replica digitals. You can do both the simulations and the actual or real process, and compare at the real-time positions. It's future optimizations of food processing. Yeah. Okay, with the simulations, you can do a temperature like 1,000 degrees Celsius or whatever you want, because it's only the simulations. You can see what happens if you do the simulations at the 1,000 degrees Celsius. What happens inside the cane? If you do the sterilization at the 100 degrees Celsius, and also you can see and you can check what happens inside the cane. That's the power of the simulations. You can do many things as you want. Okay, thank you.
Okay, we'll now have a question from the online participants. Good evening, Dr. Bayu. I would like to ask, first take, a lot of people recommended 50% cooked because it will be juicy, but there will be a risk of bacteria contamination. But if it's 100% cooked, it will lose its juicy texture. So may I know, is there any way to make sure that the steak is cooked well while maintaining the juicy texture of the steak? Okay, the question relates to this real-world application of heat transfer and moisture modeling, which intersects with Dr. Bayu's expertise, but the microbial safety aspect is in different situations. So if you're interested in the modeling side, maybe Dr. Bayu can answer the question related on that, or through the simulations maybe you have done. No, the texture maybe, because if it's cooked 50%, it will be juicy, but there will be a risk for contamination. But if it's cooked 100% or well done, maybe the texture will be not juicy. So
Okay, yeah,
what do you comment on that?
yeah, there's also another level of the simulations actually, but actually I can imagine what step that we can take to solve that problems is immediately comes in my mind. Like first we can do the simulations with the actual geometry of the meat, and then get some informations what happens inside the meat during the computations. And then we can do the multi-scale models as we did also at the micro scale levels. And we can see the structure of the meat and validate it using the X-ray computed tomography and make a correlations between, let's say the temperature or maybe some texture shrinkage with the microbial growth, and the change of the structure will probably answer or relate the simulations and structure informations as well. But yeah, we have to do some technical things to make it validated based on that method. But it's also good to work on that area as well in the future.
Okay, thank you, Dr. Bayu, for the great answers. So do you have more questions? Or okay.
Thank you for the opportunity, and thank you, Mr. Bayu, for the insightful session. And my name Amanda. I'm from Indonesia. Basically, my background is not in agriculture technology. My background is mechatronics engineering. And mechatronics engineering. And I also do testing and simulation. The name is CAD, not CAE.
Yeah. Okay.
And basically, we create 3D design, and then we select the material like steel or plastic. I just wondering, how do we identify the material properties of food? Because we know that food is more complex than steel or plastic. Yes, this is my question. Thank you.
Okay, thank you so much for your questions. Yeah, you're true that that's why I mentioned that this is challenge in food, because food, it's not stable. It's change periodically. How to get the parameters of the foods? Yeah. First, what simulations? What you want to do? It's a heat transfer simulations, mass transfer simulations, or let's say more advanced things like respiration simulations or another chemical reactions things. And then we can start, once you know what simulations you want, then you can start search for the parameters you need. And the measurement can be done experimentally, like thermal conductivity we can do with the equipment device. I don't know, here in this faculty, I think there is some, or you can, in engineering things, you can create the device to measure the thermal conductivity or diffusivity. That's one thing. And the other things, you can measure if there is some reactions in the fruits, that you should know what reaction that you want to simulate. For instance, respirations. For respirations, you need to measure, like we as a human, we respire, we consume oxygens, and we produce the carbon dioxide. The product of the fresh products also do the same things. Then you can measure the respirations of the product, create the models, and then the model parameters can be used as the parameters of the simulations. It's like a multiple step, of course. And the other things like a porosity, let's say, you can measure with the microscope, and yeah, many equipments, but it's not that easy, of course, yes, to measure the food physical or chemical parameters. Thank you for your questions.
Okay, now before we this session, I would like to take one last question from the online participants, from Fania Yuliana. Good evening, sir. Can KV modeling implementation also include optimum heat using to avoid too much energy was wasted while the process of product processing? While the process of product processing, sorry. So like, can cafe modeling implementation also include optimum heat? Yeah, optimum heat using so.
Heat during the process, you mean?
Avoid too much energy wasted
Oh,
because
yeah, yeah.
using, yeah.
Yeah, of course. Yeah. It can be used to assess the energy consumptions during the process, of course, because we can check, let's say, optimum temperature that we need actually to cook food, let's say, like to fry potato, we can increase the gas input on your stove, but it's actually consumes many energy of the gases. But if we know, if we did the simulations before, we can we can know the optimum temperature, so we can go above the optimum temperature that consumes more energy.
Okay, it's been such an engaging session. Thank you all for your thoughtful and enthusiastic questions. It clearly shows how relevant and exciting this topic is and how much curiosity it has sparked among us. Thank you very much for Dr. Bayu for the comprehensive and engaging talk. Your presentation helped us see how advanced modeling and computer-aided tools can bridge the gap between engineering theory and also practical food system solutions. Now, Dr. Bayu's Nugraha sessions highlighted the emerging role of computer-aided food engineering, or CAFE, as a powerful tool to enhance food process design, optimize quality, and also to reduce the resource usage in agri-food industry. So the key takeaways from the presentation can include the shift from trial and error to model-based design. So this traditional prototype-based food processing relies heavily on experimentation, which is costly and time-consuming, while CAFE enables model-based design using virtual simulation, reducing dependency on physical trials while accelerating innovation, and also have mechanistic models based on physical laws are used to simulate complex interaction in food system, including heat and mass transfer, microbial growth, and also structural deformation at both macro and also micro scales. And the challenge ahead is the development of cafes still hindered by the lack of multidisciplinary human resources as expertise in both food system and also computational modeling remains rare in academic and industry settings. In conclusion, computer-aided food engineering is not just a technical innovation, but a strategic pathway to smarter, faster, and more sustainable food engineering. And its successful implementation depends on both technological tools and also human capacity building. On behalf of the organizing team and all participants here and online, we'd like to sincerely thank you for sharing your knowledge and experience with us today. And now, as a token of our appreciation, we are happy to present you with the certificate of appreciation. Okay, once again, thank you, Dr. Bayu Nugraha. And we hope you enjoy today's session and gains new perspective. See you in next session and enjoy the rest of summer course. And now I'll be passed to our MC to close the session. Thank you.
And also, we would like to thank Ms. Hilda Maya Cynthia Dewi, Master of Science, who led the discussion. And certificate of appreciation will be given by the chairman of the 7 summer course program, Dr. Vyameta Ayu Purwandari. With the session of appreciation certificate already implemented, then the 5th material of this summer course has ended. For operators, you may stop the recording.